Hi, I'm Mr. V, and today I'm going to be talking about the illustrative mathematics, geometry. This is Unit 1, the second half, which is rigid transformations, and this is Lesson 12, defining transformations. By the end of the lesson, you should be able to say, I can describe a translation stating the directed line segment, and I can draw translations. The first thing we have is, what do you notice? What do you wonder? Please pause the video and type 3 things that you notice and maybe one thing that you wonder. Some of the responses of students were, I notice I have a red triangle and an orange or yellow triangle. The yellow one doesn't have any letters next to it. There's this line or line segment or directed line segment because it's got an arrowhead on it. It's called V. I wonder what this has to do with the drawing. It looks like triangle CDE is translated or moved by the same distance as V is and in the same direction as V. I wonder if this is a translation. I wonder how you describe translations. What are the properties of translations? What is the definition of a translation? In the next slide, we had something that we could play with. This is figure ABCD, and using the select tool, we can move this around. And you can see that I can move it. If I move this object, ABCD, which is here, by a directed line segment from P to Q, I can move it further away, less far away. I can make it where it matches up, but it's going to be this directed segment, and it doesn't matter where this directed segment is. It's going to take A to the one vertex, D to the other, C to the other, and B to the other. It doesn't matter if I'm going this far or however far. These will all line up. Miss Kirkpatrick talks to us in this slide, and in it, she says, find some other vectors or directed line segments that go from V to W. And here you can see I've got several of them marked in blue and some that are marked in red that are not this directed line segment. When we make a conjecture about this, we could say, well, what do we think? Maybe it has to go in the same direction. Maybe it has to go in the same length. I conjecture that they're all going to have the same length. They're all going to go in the same direction. This is not going in the same direction, and it's not the same length. It's a little bit longer than this segment. Maybe you say something about these lines, how they're all parallel to this one. That could be a conjecture. So we did this a second time, going from V to Z, not V to X, not V to W, but V to Z. Some people tried to draw them just by connecting the dots. No, the dots have to be this direction and this length. So I've connected a few here. And again, we came up with a conjecture. On slide 12, Miss Kirkpatrick talks to us about this again. And she says, notice that they all have the same length. Each one of these going from L to I, from I to C, from M to J. They all have the same length, and they also have the same direction. So all of these lines are parallel to each other, and they're parallel to this directed line segment. So they have the same length and the same direction, parallel. These arrows, which are segments with an arrowhead on it, are directed line segments, and that's the words that we'll use. Sometimes we call them vectors. Sometimes in the program that we use, it calls them vectors and not directed line segments. But it's directed because it has direction and it has length, direction and magnitude. A directed line segment conveys the direction and the distance that each point is translated. It's like walking a dog. It starts with a head, that's where it's going to, and it starts at the tail, which is where it's starting from. And yes, tail and head are the words that we use in geometry to describe the parts of a directed line segment. So here we had an exercise, and I'm going to show you this exercise. I'll walk you through it so that you can do this at your own tempo. Notice that when I pull out the tools, it covers up AC. And I'm supposed to translate this triangle by a direct line segment AC. How can we do that? I'm going to show you how. First thing I'm going to do is I'm going to create a vector, not a segment. It's the fourth tool on the bottom here. I'm going to just make it a short one, and I'll make it right above the B. So I do that so I can see it, and this is what it should look like. The next step has a few parts to it. Listen carefully. And you can rewind this to show yourself back if you get stuck. We're going to create a transformation. We have to define the transformation. The transformation we want is a translation. That's what this whole unit is about. It says to choose the point from and to choose the point to. Where we're going to go from is the tail of the vector. I will click on it once. Where we're going to is the head of the vector. I will click on it once. And then it says select some object to apply to this transformation to. So this is my transformation. Now I have to pick some object. If I click on the dot here again, it's only going to move that dot that far. I want to click on this object. So I'm going to highlight the whole thing. I would highlight the A too, but I can't see it because of the tools are in the way. So when I apply this vector from here to this, I get this triangle. You can see they overlap. Well, I'm supposed to go from A to C. So I'm going to move this around. When I do that, I get this distance. Notice if I line this up, A to C, it's right there. And point B is going to be moved to B prime, and point C is going to be moved to C prime. It's going to go that same direction. If I had moved it this way, it would be going from A to B, or could go from here from B to A, or B to C. But I'm going to translate this from A to C, and doing it by this vector. What is the relationship between B, C, and B prime, C prime? Well, they're congruent. They're congruent because they've been translated by vector AC. So segment B goes to B prime, segment C goes to C prime, in the same direction, in the same length. Therefore, distance is preserved. And how does the length of BC compare? Well, they're the same. That's what I just said. The definition of a rigid transformation is that a point can be moved to its image by a directed line segment, which will take it in the same direction and the same length. So if I'm moving point B the same direction, same length as point C, the same direction, same length, therefore these segments are congruent. Now, Ms. Kirkpatrick tells you three things that are important, and they are also outlined on the next 3 pages. I encourage you to watch her video. Here she says, the translation is a rigid transformation that takes one point to another point, one point to another point. Let's see, like this, one point to another point. So that the directed line segment from the original point to the image is parallel to the given line segment, which is V, and has the same length and direction as V. That's what a definition of this, and this should be added to your reference document. 2 days ago, we received this in lesson 10. So if you go back to lesson 10, you can download your copy of the reference document if you've not yet done so. We'll use the reference document throughout. Here's the second big idea, parallel postulate. If you have a line and a point not on that line, there's exactly one line that goes through this point that's parallel to this line. And this is called the parallel postulate. When Euclid wrote his book, The Elements of Geometry, he had 5 axioms or postulates. And we have several more today, but he had 5. And the 5th one, which is this parallel postulate, has given scholars a lot of things to talk about throughout the years. And like Ms. Kirkpatrick says, if you don't believe this, all of Euclidean planar geometry falls apart. And there are whole fields of geometry, which is like spherical geometry or other types of geometry, that don't assume this, assume something else, and have different rules altogether. We're not studying any of that. All we're studying is the planar geometry, one line that's parallel through this line, to this point, to this line. The third idea is that lines transfer to other lines, translate to other lines that are parallel to the original, or they translate to themselves. So if this vector v was a long line m, it would translate to line m. Here's I needed to go back. Let's see here. I will delete this and show you. If I were to translate, transform, define the translate, I'm going to go from this point to B. I'm going to translate this object. Excuse me, I need to define the transformation. From this point to B, I'm going to translate this object and apply it. You can see that these lines are parallel. And the big idea is that there's only one line that goes through B that is parallel to M. And that's what we're doing. There are infinite lines that go through B, but only one of them is parallel. Here's the summary. You can read it. It tells you about directed line segments. It's important. And finally, Priya. She makes a terrible mistake. What did she do that did not get her where she needs to be? Please explain that, and then tell me how you're feeling about today's lesson. Good luck and success.